Welcome students. Today we'll talk about cylinder and quadratic surfaces or quadratic surfaces. So let's start with this quote by Isaac Newton, who needs no introduction really. The description of right lines and circles upon which geometry is founded belongs to mechanics. Geometry does not teach us to draw these lines, but requires them to be drawn. Okay. So what is the goal of this lecture? So we want to recognize certain quadratic surfaces. We'll discuss in a minute what those quadratic surfaces are, and then we'll sketch the quadratic surface given its equation. So main tool here we'll use is contour curves or the traces. And these contour curves will be usually conic sections for our quadratic surfaces. So the idea is we need to understand what conic sections are. So this shape is cone. It's a two-sided. It's actually the cone, but you can think about it as two-sided cone. Now, depending on where you cut the cone, aka where you take the section of the cone, you get different geometric objects. Say, for example, if you cut it in a plane perpendicular, you will get, or in a horizontal plane, you'll get a circle. Yeah. If you cut it in a plane slightly slant like that, you will see that it cuts in an ellipse like that. If you cut it in this direction like this, in a plane this form, you will get a parabola. And if you cut it spanning through these two parts, if you cut it like this, and this cuts through both the parts, the intersection will be a hyperbola. So these sections are called conic sections. They each have interesting shapes, and accordingly they have equations. So first example of a conic section is circle. Yeah, so circle is obtained by cutting it horizontal. In a horizontal plane, you get a circle. It's usually given by x squared plus y squared equals to a, and that represents a circle of radius a. Right, so we have a circle of radius a. So we have circle of radius a, so this part is going to be a. This is given by x squared plus y squared equals to a squared. So this is circle. Then we get what is called an ellipse. If we cut in a, as we already discussed, if we cut in a plane just slightly slant, an equation of an ellipse is given by x squared plus y squared equals to 1, and x squared by a squared plus y squared by b squared equals to 1, and the ellipse looks like this. And if we draw it, if you look at the ellipse x squared by a squared plus y squared by b squared equals to 1, then we have this point is going to be a0, 0b, and so on, minus a0 and 0 minus b. So this is your ellipse. Circle. Now another interesting cross section is parabola. We have seen the parabolas of this form, right, which are given by y square, or sorry, y equals to ax square. The parabola mentioned here is, so x and y are inverted. So we have parabola of this form given by y square equals to 4ax. So this is a parabola. Another interesting cross section is a hyperbola, which is given by x squared by a square plus, sorry, minus y squared by b square equals to 1. You can see the similarity between the equation. So ellipse equation and hyperbola equation, you have a difference is here there was a plus, here there's a minus, and this is how it looks like. This point corresponds to minus a, this point corresponds to a. So this is a hyperbola. So of course, this is not a complete discussion on conic section. I mean, we can dedicate more time in class. However, these are the conic sections. Right. So what we want to study in this section is cylinders and quadratic surfaces. So essentially, we want to study a surface in 3D. So the easiest of all, or the easiest to understand, is a cylinder. So what is a cylinder? So cylinder is a surface which consists of lines that are parallel to a given line and passes through a given plane curve. So let's look at an example of a cylinder where we have, so let's look at this cylinder. So this is x, this is y, this is z. And consider the cylinder x squared plus y squared equals to 4. So then that is, if you look at that, that's going to be a circle in xy plane to start with, and then we can extend it. So this is a circle in xy plane, and what you have is, but z is all the possibilities. So essentially what you have is, you have, so cylinder consists of lines that are rulings parallel to a given line passing through the plane curve. So your plane curve here is x squared plus y squared equals to 4. And you are drawing, so we are drawing lines which are parallel to this given line. So for example, we have then you'll have things behind too. And I would like to draw the background line with dotted blue. So I get a cylinder. This is the axis. So axis is z axis for this cylinder. And then these are the rulings, right? All these lines are the rulings. So essentially you have surface consists of lines that are parallel to given line passing through the plane curve. So your plane curve is x squared plus y squared equals to 4. And these are the rulings. Of course, they both go in both direction. All right, so they go up as well. Now let's look at the following. We have the following cylinder. So y equals to z square. Now, how is this a cylinder? So let's first draw the axes. So y equals to z square. The graph looks like, so y equals to z square. So we have y equals to z square looks like the following curve. So of course it keeps on going up forever, and then we are drawing lines which are the rulings. So essentially we'll have rulings here. Of course we are drawing only the part of it. These are the rulings. I should erase the ones which are the background so that to give a proper. So these are the rulings on this side. And as we can see, this is also a cylinder. Okay, it keeps on going in this direction forever and also up. Yeah, so y equals to z squared is this big thing, right? So this is another example of a cylinder. Okay, so these are so-called cylinders. Ruling goes all the way like that, and then we have things at the background go like this. So these are cylinders. So essentially the idea is if you have a curve and you have certain axes to which you are looking, you're going to draw lines parallel to, then it will be collection of all these join them, then you join these parts. So these are the rulings. Yeah, the rulings are also on the other side as well. Okay, so that is the idea behind the cylinders. Okay. Now, the next surface we want to discuss is the quadratic surface or quadratic surface. So what are quadratic surface? So they are given by general second degree equation in three variables, x, y, and z. So we have ax squared plus by squared plus cz squared plus dxy plus exz plus fyz plus gx plus hy plus iz plus j equals to 0. So all possible mixing of x and y, x, y, and z is there. Only thing is that we have the degrees to be 2. Yeah. So this gives a quadratic surface, and the classification of them is easy. We have already classified them here. So now if you do change of variables, you can basically bring them to one of these forms: ax minus x squared, ax squared plus by squared plus cz squared plus j equals to 0, or ax squared plus by squared plus iz equals to 0. Yeah, you see the difference you have. Yeah. So if by doing certain translations, rotations, you can bring it to either one of these forms. Now, why do we mention that? The reason for mentioning that is that we can then study, we can focus on studying these guys. Yeah. Now note that say for example, if you had x minus 1 square plus y minus 2 square plus z minus 3 square equals to say 2 square. This is also your quadratic surface, and you know that it gives a sphere of radius 2. Now what is happening in this case is we are transforming, put x minus 1 as capital X. So we are basically replacing it by capital X square. Similarly, put y minus 2 as y and z minus 3 as capital Z. So this becomes x square plus y square plus z square equals to 2 square. So this is the kind of transformation we are talking about. So using this transformation, we can study then, once we get to this thing, we can study all kind of quadratic surface by doing translations and studying one of these. So how do these objects look like? So one is an ellipsoid. So equation of an ellipsoid is given by x by a square. So x squared by a square plus y squared by b square plus z squared by c square equals to 1. So this is the equation of an ellipsoid. Now we want to understand this object through traces. So what are the traces? So traces are generally you're cutting x equals to z equals to k, y equals to k, and x equals to k. And then you try to study what kind of object do you get. So let's start with z equals to k. So if you have z equals to k, for example, then you will get, if you cut z equals to k, you will get an ellipse, right? So this is basically cutting it, say z equals to k. You're cutting a slice. Similarly, if you cut it in, so this is z equals to k. Similarly, if you cut in x equals to k, that means you're cutting a slice like this. And already some of the traces are drawn. So each of this is a trace, and you see that they are also ellipse, yeah, of varying size depending on where you cut it. So all the traces are ellipse in this case. You can see other way around too, right? If you cut y equals to k, so now I have to erase this because it get too messy. If you cut y equals to k, so you're cutting y equals to k plane like that, you will get essentially, if you're cutting it in a y equals to k plane, so this is a plane, and when it cuts, you slice it through. This is the intersection of it. This is the background, so should draw it with the dotted part. So you get an ellipse as well. So all the traces are ellipse. Now note that if A equals to B equals to C, then your ellipsoid is a sphere. So all the traces are spheres. Oh, sorry, all the traces are circles. So ellipsoid can be thought of as a, or rather, sphere can be thought of as a special case of ellipse or ellipsoid, where A equals to B equals to C. All right. Now let's look at the next one. Z by C equals to x by a square plus y square by b square. So what are the traces here? So again, suppose you say, well, z equals to k. So you get k by c equals to x square by a square plus y square by b square. Now that is an equation of an ellipse. So z equals to k, if you cut it, z equals to k, we will get again an ellipse. So the horizontal traces, those are called horizontal traces. So z equals to k is called horizontal trace, is horizontal trace. And the other two traces are called vertical trace. Yeah, because for the obvious way, they look like x equals to k and y equals to k are called our vertical traces. So now let's try to look at the vertical traces. So if we look at vertical traces, that means we have to cut it with a plane y equals to k, suppose. So you're cutting with the plane, all right? So y equals to k plane. So you basically have, we have y equals to k plane. This is y equals to k plane, and if you cut it, you will see that we get a parabola. Similarly, if you cut it in the other plane as well, x equals to k. So let's try to cut it in x equals to k. So x equals to k would be, take x equals to k. So here's the value k. And then when you cut it like this, we again get a parabola. So such a thing is called elliptical paraboloid. So we have z by c equals to x squared by a squared plus y squared by b squared. We get a paraboloid. Now that can be seen also from the equation too. It's not just cutting it. You can see that from equation. So suppose you let x equals to k. So if we have x equals to k, this gives us z by c equals to k squared by a squared, some constant, plus y squared by b squared. So z equals to some constant, some y square plus a constant. So that is a parabola. So z equals to y square is a parabola, all right? Next one is called a hyperbolic paraboloid in this case. So we have z by c equals to x squared by a squared minus y squared by b squared. Why is it a hyperbolic paraboloid and what? So let's first ignore this graph for a second. So suppose I have z equals to c. Then if z equals to c, then this will become 1. And you can see that at z equals to c equals to 1, when you cut it with the z equals to c plane, if we cut it, we'll see that it's going to be, so we'll get a hyperbola. So if we cut it z equals to c, so horizontal traces are hyperbolas. What about vertical traces? So for vertical trace, let's cut it vertically. So if I cut vertically anywhere, so I'm going to cut it now vertically directly. So vertical traces are, so if you cut it in y equals to k, you get a parabola, inverted parabola, but nevertheless a parabola. And even when you have x equals to k, when you cut, you get a parabola, right? So such a structure is called hyperbolic paraboloid. Now comes the cone. We have already seen when we are looking at conic section. So we have z squared by c squared equals to x squared by a squared plus y squared by b squared. So if we let this to be constant, so we have x squared by a squared plus y squared by b squared equals to some constant k. Actually, we are already looking at z equals to k, right? So it's some constant a. Then you can see that it will be again an ellipse. So if I'm cutting in a horizontal setup, I will again get a, I'm again getting an ellipse here. However, if I cut it vertically, what structure am I getting? So vertically, if I cut it, then I'm getting essentially hyperbola. So vertical traces in plane x equals to k and y equals to k are hyperbolas if k is not 0. But if k equals to 0, suppose if k is 0, then what do I get? I'll get pair of lines, right? That's not hard to see either, because if you cut it in this thing here, say, let's cut it in x equals to, let's cut it x equals to 0. So if you cut it like that, you'll be left with one line. So one line which goes like this, the other line which goes like that. So we get pair of lines. So such a object is called cone. Again, you see, just by, even though we didn't need this geometry, we'll see how we can look at the equation and attempt to draw the graph of it. Next interesting object is hyperboloid of one sheet. So it is one sheet and it's a hyperboloid. You see hyperboloid of two sheet means there are two disjoint structure. So let's see how does it look like. So we have x squared by a squared plus y squared by b squared minus z squared by c squared equals to 1. So now the way to understand this is take this to be k. Let's look at the horizontal traces. So then you will have x squared by a squared plus y squared by b squared equals to some constant k, 1 minus k squared by c, right? So that is equation of an ellipse. And as you can see, all the horizontal traces are going to be ellipse. All the horizontal traces are ellipse, right? Now, what about vertical traces? So vertical traces of this. So what are the vertical traces of this? The vertical traces are, if we look at the vertical trace here, we'll see that that is a pair of, so that is a hyperbola. And that you can also see from the, that we can also see from the equation too, right? Because if say you take x equals to k, if we have, if x equals to k, then we get y square by b square minus z square by c square equals to 1 minus k square by a square, which is some constant, right? So you get basically a hyperbola in z and x, z and y. So it will be a hyperbola where you have y-axis and z-axis, and it will be like that. Yeah. Similarly, we have hyperboloid of two sheets. All right. So now we are good to go for the, so this figures, I mean, I'm using quadratic or quadratic surface interchangeably. They are the same thing essentially. Then you may also ask, why only quadratic surface? Why not if the power is 3 or power is 4? Well, we may not be able to draw it in all the cases. One, yeah, the structure may become slightly more complicated, right? But nevertheless, and also the ideas we learned here are generalizable. So for example, if the slice is a cubic equation, then it will look like a cube, right? If the section is cubic equation. However, so we'll restrict ourselves to the quadratic surfaces, baby steps. So now let's look at the following. X squared by a squared plus y squared by 9 squared plus z squared by 6 equals to 1. And let's understand what it is. First of all, if you compare it with the known equations, it looks like it is of the following form. So it is an ellipsoid. Right. However, how do we get to it? So consider the step 1. Let's take trace z equals to k, the horizontal trace. So horizontal trace z equals to k will, when you put z equals to k, you get x squared by 4 plus y squared by 9 equals to 1 minus k squared by 6, which is an ellipsoid if what? If this is greater than equal to 0. If it is equal to 0, then you get a point, right? It shrinks when basically absolute value of k grows, and absolute value of k is less than equal to 6. Otherwise, this will become negative, and then you have sum of two squares, which is negative. That is not possible. So there are no solutions then. So let's draw this thing. So let's see, when z equals to x, y, z. Say when z equals to 0, what do we get? So when z equals to 0, we get x squared by 4 plus y squared by 9 equals to 1. Yeah, so z equals to k. So in that case, we get a parabola, sorry, a ellipse here in xy plane because z is 0. So here we'll go 1, 2, here we go 1, 2, 3. Then let's just draw it. So I drew this parabola, sorry, ellipse for the trace k equals to 0 in the horizontal. Now, as we go up further and further, so this should be drawn with the dotted because it's not in the front. Now, if we go up, then we get a smaller, the size of this thing shrinks, right? So take say z equals, so k equals to say 2, then the size of this will shrink, right? So these sizes shrink, right? So we get basically ellipses on top of each other. Now, what about the trace in YZ plane? So if you take YZ plane, so this is your X, this is the Y and Z. In YZ plane, that is in this plane here, this is Z, this is Y. In YZ plane, it's also an ellipse. So YZ plane, we have y squared by 9 plus z squared by 6 equals to 1. Your x is 0, right, in YZ plane. So your x is 0, and the YZ plane we have essentially an ellipse. Yeah. Now similarly, the trace in XZ plane, what happens in XZ plane? XZ plane we get XZ plane, we have this equals to 0. So we again get an ellipse in the plane, right? So when you draw all the traces, all the vertical traces are also ellipse. All the horizontal traces are also ellipse. And we end up with an ellipsoid. So the second example is y equals to z squared plus 6x squared. So before we look at the known graph from our catalog, let's try to see what do we get out of this. So y is z squared plus 6x squared. So consider the trace y equals to k. So y equals to k, z squared plus 6x squared equals to k is an ellipse, right? It's an ellipse of form z squared by square root of k the whole square plus 6 by square root of k by 6 x upon x squared by this equals to 1. Yeah, so this is an ellipse. And as your ellipse k keeps growing, your ellipse will also expand, right? So notice the case when k is 0, you get essentially 0, right? So you have when k is 0, we have a point. Let's say when k is 1, so y equals to k is 1, we get z squared by 1 plus x squared by square root of 1 by 6 the whole square equals to 1. So it's going to be an ellipse in, so we have x plane, y plane, and z plane, right angle according to right hand rule. And we have, when we take x equals to trace k, we'll get in this x equals to k trace, we'll have an ellipse. And this ellipse has bigger for z and smaller for y, right? So z is bigger. And then as you keep going bigger and bigger for k, your ellipse basically expands like that. Okay. All right. Now the traces in YZ plane, so this is your YZ plane, is basically a parabola y equals to z square. So y equals to z square looks like this. So if we cut it in this plane, YZ plane, it's basically a parabola. So let me draw that. Increasing parabola. Okay. Similarly, in ZXZ plane, you have, well, you have then y equals to 0, you get a point. How about the other one, which is, so we have taken YZ, and then let's talk about XY plane. So in XY plane, your Z is 0, you get y equals to 6x squared. So in XY plane, your y equals to 6x squared, which is also a parabola in YZ plane. So it will look like so this is in your XZ in XY plane. Okay, so let's join these nicely. So we see that we are getting a shape of a it's like a so this is an example of an elliptical in one and then paraboloid otherwise, right? In other two sections, it's a parabola. So paraboloid. Yeah. So this is the, if you look at the catalog, this is a, sorry, this is the diagram we got here. We got an hyperbolic paraboloid. Sorry, in this case, we get elliptic paraboloid. What am I saying? So idea is you get this ellipse in one trace and other two traces are parabolas. So we call it elliptic paraboloid, and this is the structure you get, except for the fact that instead of z-axis, you have what? You have z-axis replaced by y-axis in this case. Now let's look at the next example. We have z equals to 4x squared plus 4y squared. So again, if you take x equals to k trace, we get 4x squared plus 4y squared equals to k squared. This can be written as x squared plus y squared equals to k squared by 4. And when k, so we get, in this case, we get, so not k square, it's k. So we get k, and note that there is no trace when k is less than 0, right? So k has to be greater than 0. K can be negative, k cannot be negative, right? Why? Because if we take k to be negative, there are no solutions, right? So this is not true. K cannot be, so let's say k cannot be negative, right? So k cannot be negative, and then we have, let's draw this. So we are drawing the horizontal traces now, z equals to k. So let's see, so when k is 0, we get what? A point, right? We'll get this point. When k is 4, we get, if k equals to 4, this gives us, sorry, k equals to 4 gives us x squared plus y squared equals to 1. So k equals to 4, we have a circle there. And then for smaller case, we have smaller circle. These circles keep on growing in sizes. We have a point here, then we have slightly bigger circle, then the circles get bigger, then they get bigger, then bigger, okay, so smaller. So this is how it looks like in z equals to k. Now what about in yz plane? In yz plane, we get z square equals to 4y square, or we get z equals to 2y. So we have x, y, z. So in z equals to y plane, it's a line, x equals to 2y, which is this line here, or x equals this line here. Yeah. And similarly, you can see the other one as well. It'll be lines. For the other ones as well, we'll have a line. So this shape is, so this should be drawn with the dotted because it's the background. So let's just draw this with dotted. Okay. So this looks like a cone to us. So it is indeed a cone, which is given by this equation here. So it is well, it can be also called elliptic paraboloid because the bottom part is missing. So we can call it, if you want to give it a name, we can call it circular. So circle is a special case of ellipse, right? So we can call it circular paraboloid. Yeah, these lines are like a parabola, really, right? So circular paraboloid. Now let's look at the following problem. Again, we have z squared by x squared by 4 plus y squared by 2 minus z squared by, sorry, y squared minus z squared by 4 equals to 1. So we want to understand this equation. So again, first we'll look at the horizontal traces, which is z equals to k. When you substitute z equals to k, you get x squared by 4 plus y squared by plus y squared equals to 1 plus k squared by 4. Now, what is this? This is an ellipse, right? It's an ellipse. And as k increases, the radius will increase. So it keeps growing as k increases. Right, so we have the following. So let's draw this, at least the trace. So when we have x, so when we have k equals to 0, we will get, so this is your x-axis, this is your y, and this is your z. So when k equals to 0, you will get x squared by 4 plus y squared equals to 1. So if k equals to 0, then we get x squared plus y4 plus y squared equals to 1, which is an easy ellipse to draw. So we get an, here we have 1, here we have 1. Okay, so this is the k equals to 0. And as k becomes larger and larger, the size of ellipse also goes bigger and bigger. So this was at k equals to 0. When k is 1, when k becomes bigger, the size of the ellipse will also become bigger. Right? However, in xy plane, so xz plane, in xz plane, x and z plane, in this plane here, xz plane, it is essentially we get x square minus z square equals to 4. So we get essentially a hyperbola like that. Similarly, in yz also we get a hyperbola. Then let's join them nicely. So this looks like a hyperboloid of one sheet. So if I draw it in a slightly different perspective, this is how the shape will look like. Okay. Yeah, so hyperboloid of one sheet. So with the trace, we are able to construct the whole graph. Right. Okay, so now consider the following problem. So a cooling tower for a nuclear reactor is constructed in a shape of hyperboloid of one sheet. It looks like this. The diameter of the base is 280. So diameter of the base is, so we have a hyperboloid of one sheet. So let's just draw that. So this is a hyperboloid of one sheet, and the diameter of the base, or the radius of the base, is essentially given by 140. Okay. And the minimum diameter, which is 500 meter above the base, is 200 meters. So above, so the minimum diameter is somewhere here. And in this case, the height here from this part to this part is 500. And the radius for this guy is, so diameter is 200, so the radius is 100. And now we want to find out what is the equation of this hyperboloid. So if we go back to our catalog, we know that the equation of such a hyperboloid is x square z square by c square equals to x square, no, my bad, x square by a square plus y square by b square minus z square by c square equals to 1. So we can write it down. So we have x square by a square plus y square by b square minus z square by c square equals to 1. Now, how do I decide? So note that in horizontal plane, it's an ellipse. So it makes sense that the minus sign is here. Yeah. If the minus sign is somewhere else and the others are plus, it will still be a hyperboloid of one sheet, but the thing will be tilted. So that's that. Secondly, note that when z is 0, we know that it's a circle, right? So we know that A equals to B, and that is equal to, so when z equals to 0, so let's say, so when z equals to 0, we are here, right? Because that's defines the smallest circle. We have x square by a square plus y square by b square equals to 1. But this is a circle of radius. So it's a circle. So we have a square equals to b square. That is x square by y square equals to a square. So a is 100 in this case. So we got a equals to b equals to 100. So we are getting close. So our equation is x squared by 100 square plus y squared by 100 square minus z squared by c square equals to 1. Now, how do we go about this? So now we want to find out what is c, right? So the idea is if you take z equals to 500 or minus 500, so z equals to minus 500, So z equals to minus 500. Then we get what? X squared by this square plus y squared by minus 500 square by c square plus, sorry, equals to 1. And then if you replace it, we get x squared plus y squared equals to 100 square times 1 minus 500 by c square, 500 square. Now this should be equal to 140 square, because at z equals to minus 500, it's a circle of radius 140, right? So the radius, this should be equal to your r square, which is 140 square. So this should be equal to 140 square. Now we want to solve this equation. So we want to solve, so 100 square times 1 minus 500 square by c square equals to 140 square. So if we do the calculation, this will give us, so this gives us 100 square plus 50,000. So, so 50,000 square by c square equals to 140 square. So this means, this gives us, so if I solve for c, so c square equals to 50,000 square divided by 140 square minus 100 square. That is going to be, if I use the calculator, so I get 781,250 divided by 3. And therefore, I get the equation is x squared by a square, which is 100 square, plus y squared by 100 square equals to, or minus z squared by c squared. Now I'll write it as 250 divided by 3 square root, the whole square, equals to 1. And my z is between 500 to 500. Yeah. You may say, well, it doesn't look like it goes all the way up, but we are assuming the structure to be symmetric like that, right? So the way, exactly the midway. Okay, so this is the equation of this cooling tower. Very neat, very cool. Thank you.